Hi, I'm Chris with Sanderson Test Prep, and in this video we're going to take a look at the relationship of tension as a force and both mg and force of friction. So when we're dealing with tension, tension is a force of a string or rope pulling on a certain object. And one of the most common tension questions that we get introduced to, where we start having questions about tension, usually when it's two objects and just a string directly between them on one axis, horizontally or vertically, that's where the understanding of tension seems to be pretty straightforward. But then when we start getting into situations where we have a horizontal and a vertical component, that's when a lot of times it seems like it's more difficult. And it's really not so bad if we remember one key point. So let's take a look at this sample question and let's see if we can figure out what that key point is that's going to help us handle tension questions. So here it says, what is the force of friction on a 10 kilogram block at rest on a table that is attached to a hanging block of mass 20 kilograms as seen in the diagram below? So as with any diagram that we have in physics, a really good habit to get into is drawing out a free body diagram for each object. And here these are spaced far enough apart so we can draw in the forces acting on these two objects right here on the objects where they're located. So here we're going to have an upward force due to tension and a downward force due to mg on this block. And for our purposes here, since we do have two masses, I'll call this one mass 2, so m2g. And the forces at work, since the block is at rest on the table, that's important to note because that means you are going to have this same force of tension. All right? Tension is pulling that block towards the right, and those two values of tension will be equivalent to each other. So there must be some force opposing that tension, and that's the force of friction. So that's going to be your force of friction pulling the block on the table towards the left. So now if we need to figure out what that force of friction is, we can look at each block individually and recognize that if everything is at rest, that means acceleration is 0, net force is 0, which means that these two forces acting on each block have to cancel each other out fully. So for block 1, we know that the force of friction is equal to the tension. And for block 2, we know that the tension is equal to m2g. And if we use a little bit of substitution here, we can plug in for tension and relate these to each other. So for this, we're going to have force of friction is equal to m2g, and to calculate that, our force of friction will be 20 kilograms times, and it depends what you're using. Sometimes in class your teacher might round it to 10, but to be perfectly correct on this, we'll use 9.8. So when we multiply by 9.8 times 20, we get 19.6 newtons as our force of friction. And that is, in fact, our final answer for the force of friction that this block is experiencing on the table. So that seems pretty straightforward because they're asking for force of friction as a whole. And when they're asking for force of friction as a whole, like we see in this question, then that calculation is going to be a little bit simplified, just like what we see here. So let's take a look at a slightly more complex question and see how we would address that one. So what if they're not asking you to just come up with the force of friction, but what if they're asking for a particular piece of the force of friction? So here, for example, if you were asked for the mass of that block on the table, and you were given this value mu s, which is our coefficient of static friction, then we're going to still draw out the free body diagram similarly, but we're going to have to do a little extra piece here calculation-wise. So let's start with the free body diagram. We know that we have mg on this block pulling down and then a tension pulling up if this block is at rest. We know that for the block on the table, we've got a tension pulling to the right, and then we've got a force of friction, which is opposing that. And so here, similar to what we did on the other question, we can say that if these blocks are at rest, we know that for the first block, the force of friction is equivalent to the tension, and we know for the second block, the tension is equivalent to m2g. And we could substitute in for tension just the same way we did in that previous question, and go ahead and solve accordingly if we needed to find the force of friction. But there's an extra step here. Force of friction will be equal to m2g, but they don't want the value of the force of friction in this case. They want something a little more specific. They want the mass of the block. So here, to find that mass of the block, we have to know a formula for force of friction. And I'll put this in red because it's a really important formula for us to know in physics in general, but especially when you're dealing with tension, inclined planes, moving objects across a surface. You're going to see this equation come up quite regularly. And your force of friction is equal to mu times your normal force. And the reason that that's important is because, and we're going to have to, if we're looking at a normal force, we're going to have to look at some additional forces on this block. We have our normal force pointing up, and we have m1g pointing down. And this is where we will be able to solve for mass, because just like we set these original equations equal to each other for force of friction and tension and m2g. So for this question, we have to do one more equation where we're setting forces equal. The upward normal force and the downward force due to gravity have to be equal. So your normal force is equal to m1g. And that's the important added component of this question, which has made this question a little bit more difficult. So now we can use a little bit of substitution. Our force of friction is mu s times our normal force, which is equal to m2g. And our normal force, as we said, was equal to m1g. And here we can simplify a little bit by canceling out our values for g, and then we can plug in the values given in the question and solve. So to do this, we get 0.4 times m1 is equal to m2, which is 20 kilograms. And when we divide, we get m1 is equal to 20 divided by 0.4. And that will give us a value of 50 kilograms for that mass. So in order for that block on the table not to move with that coefficient of static friction, it means that that block would have to weigh 50 kilograms for this system to remain at rest with that given value of mu s. Now when we talk about mu s, where does that value come from? So that's going to be dictated by the material the block is made out of, by the surface that it's on. And your coefficient of static friction is basically a numerical or quantitative way of analyzing how difficult it is for something to slide over a surface. So if this were a block of ice along a very smooth wooden table, then you would expect to have a very low value of mu s, because that friction is going to be limited. And if mu s is a component of your friction force, then we expect something that's not going to experience much friction would have a very small value. Whereas your value for mu is going to increase if you had, for example, something that was a little bit rougher on the bottom, maybe like a cinder block, and it was on a carpeted table. Then to drag it across, there's going to be a lot more friction involved, and you'd expect a higher value for mu. So if you're wondering where mu comes from, mu is dictated oftentimes by the kinds of materials and the way that they are mechanically going to pass over one another to determine what that coefficient of friction is going to be. If you want to take a look at some more complex questions when we have a system that's not at rest, please check out our other videos, and thanks for watching.